So here is a discussion of the quiz. I posted explanations, and this is our written explanation, or excuse me, a verbal explanation. So as you're looking at a periodic table, this happens to size as you go down the table. So as you go down to family, atoms get bigger. As you go across, this is period 1, so there's only helium in that, so it wouldn't be much smaller. As you go across, the atoms get progressively smaller. You get the idea. All right, so if you're looking at these 4 elements, the one that's going to lose the electron the easiest is the one that is holding the electrons less. So which one of these 4 elements would have a lesser hold on electrons? So looking at the position on the table, magnesium, if this was hydrogen and this is lithium and that's sodium, magnesium is sitting right here. So that's Mg. If you go across, or to the left here is sodium. So sodium is this guy right here, Na. And then aluminum is still further over here, still smaller. And potassium is sitting right here. So which one of those is the biggest? It's potassium. All right, so the answer to that one was C. But then why? Because as you move down, you're really adding energy levels. As you add energy levels, the inside electrons repel the outside. They push away on the electrons that are sitting out in the outside of the atom, so right here. So the insides push that guy away. It makes it easier to lose. So what that does is it makes the atom bigger, easier to lose electrons, which means that ionization energy is going down. And electron affinity is going down, as is electronegativity. So as you go down, electronegativity, ionization energy, electron affinity, all go down. They decrease as the size is increasing. So the repulsion of the outer shell, the pushing away, is called the shielding effect. So the inside electrons shield the outside from the nucleus. So the answer to that was D. And we just talked about this one. The halogens, of course, are over here. Fluorine, and chlorine, and bromine, and so on. As you go down, the atoms are getting bigger, so they're less electronegative. Think about the lab. What was the more active? The halogen that replaced the others was the smallest. We had fluorine and chlorine and we had chlorine and bromine and iodine in the lab. Chlorine replaced both the bromine and the iodine. So it cooked them out. That's why the top layer, remember your test tube, you had a layer on the bottom, layer on top. If that layer was purple, that meant the iodine got kicked out. All right, so as atomic numbers of the halogens increase, means you're going down, they're less likely to gain electrons, their electronegativity decreases. All right, now ions formed by the gain of an electron. Now, a gain of electron is electron affinity. So the energy change when you add an electron is known as the electron affinity. So it is negative for most atoms. So what that means is energy is released. So if energy is released, then you go to a lower energy state, which can be thought of as being more thermodynamically stable. If you add an electron, and most of the time, energy is released. However, for S2, like up here, this is S2, magnesium, beryllium, and so on. It's supposed to be Mg. As you go down, as you go into S2, when you add an electron to that, the energy is required because the sublevel is already full. So S2 and P6, that's over here with the noble gases, helium and neon and so on. Those guys require energy to add an electron, so it's positive for these guys. So it doesn't tell us what element we're dealing with, so we can't tell because we don't know if you're adding to an S2P6 or you're adding to some other element on the periodic table. Like if you add an electron to potassium, energy will be released. But if you add it to magnesium, energy goes in. If you add it to aluminum, energy is released. Most elements release energy when you add an electron. Okay, Electron affinity within a series is as you go within a series, you're going across. So in general, as you go this way, the atoms are getting smaller. Remember up here, they're smaller. So as they get smaller, there's going to be more attraction for electrons. So we would say that it increases, the affinity increases, which means it gets more negative because the more energy is released, the more energy that is released, the greater the increase in stability for that particular atom, and the more it, quote, wants to gain electrons. All right, looking at number 6, the most probable oxidation state of calcium. Calcium is in this family, the S2 family is down here. So it's going to lose 2 electrons. Remember the rule was 4 electrons in the outer shell or less, and they tend to lose. 5 or more, and they tend to gain. So calcium has 2, it's going to tend to lose them. So if you lose 2 electrons, your charge is going to be +2. That one's not listed, so the answer was D. Number 7, you do an experiment which involves adding an electron to K. Well, K is up here, it's in S1. So remember, negative for most elements. So electron affinity will be negative for potassium because it's not an S2 or P6. So the ion then would be more stable. Now remember, the ion is what you get after you've added the electron, it has a charge. Okay, which one's the most metallic on number 8? Here are their positions on the table. You got S, it's underneath O, you've got F here, you got Cl here. The ones furthest down and to the left are the biggest. Big metals tend to lose electrons, so the answer is sulfur, which has a larger radius, rubidium or rubidium ion. Rubidium sits over here. You get rubidium and then cesium. So rubidium is going to lose an electron when it makes an ion. If it loses an electron, it's got to get smaller. So this one is the bigger one here because it hasn't lost its electrons yet, or its electron yet. And this one is a smaller one. Because you lose an electron, you get smaller. Number 10, which one's going to lose electrons? This is kind of like this question up here, except it's the same idea. The most metallic lost electrons the easiest. So these are the 4 elements, the same 4 elements right here. So sulfur is the one that's most likely to lose right here. The little low-pitched whine you're hearing in the background is my dog requesting to go outside. All right, but he just wants to go outside and hang out, so I'm going to make him wait a minute. Okay, number 11, low ionization energy. Ionization energy is the energy required to remove an electron, so that would be easier or lower for big atoms. Well, big atoms are on the left side of the table. Those are the metals. So there's your answer. So as you go to the left, the atoms get bigger, which means they lose electrons easier, so their ionization energy will decrease. All right, number 12, which one has the same pattern as as atomic radius? Atomic radius gets smaller as you go to the right, but electron negativity, electron affinity, and ionization energy all got greater as you went to the right. So I'm trying to get you to see that none of these match atomic radius. In fact, they are all opposite in trend. All right, number 13, if energy is absorbed, then you're going to a less stable thermodynamic state, higher energy state. 14, an atom which gained energy. So energy went in. Now remember up here we said that energy had to be put in sometimes when you add an electron. We know that energy is always put in when you remove an electron. So since you don't know what the element is, you don't know if it's an S2 or a P6 or not, there's insufficient information to answer that question. 15. A positive electron affinity would mean energy in. So that would mean an S2 or a P6. Well, this one is an S1. This one is a P5. This one is a P4. Whoops, P4. This one is a P5. So none of those are S2, P6. So the answer is E. Now, I'm hoping you remember what S1, P5, and so on means. So, first column is S1, then the second column is S2, You skip all the short rows. Then it's an S2P1 and P2, S2P2, S2P3, S2P4, S2P5, and S2P6, like that on that. Those are the main rows. So you can only have 8 in the outer shell, 6 and 2. 16, compared to the stability of the original atom, the stability of the ion formed by the loss of electrons. Losing electrons, ionization energy. So that means energy has to be put in. So you always put energy in, always less. Okay, so ions are less stable. Positive ions would be less stable than their regular atoms. Okay, the largest. Now this is that one about protons and electrons. So 10 protons, 9 protons, 11 protons, 12 protons. Electrons, 10 electrons, because there's no charge, they're even, but this is an F minus, so that's 10. Na plus, you've lost one, it's 10. Na plus 2, you've lost 2, it's 10. So they all have 10 electrons. So the one that's the largest is the one that will hold its electrons least tightly, because electrons are moving, they want to get away. So it's going to be the one with the fewest protons, and that's going to be fluorine. All right, next one, oxygen bonding in a 1-to-1 ratio. Here is an atom of oxygen. It's got 6 valence electrons. 1, 2, 3, 4, 5, 6. So it has 2 open spots. There'd be a spot right here for an electron to go in and a spot over here for an electron to go in. So you look at these atoms. Which of these has 2 electrons in its outer shell so that one of them could combine with 1 oxygen? See, magnesium could take this 1 electron, put it in right there. And the other electron from magnesium could go in right here. So magnesium works because it has 2 electrons in the outer shell. Let me show you with dot diagrams. So it's 1, 2, 3, 4, 5, 6, 7 for fluorine, 1 for sodium, 2 for magnesium, 3 for aluminum, 4 for silicon. So if you're trying to do this, just picking another element to show you how it would be different, if you use sodium. See, sodium has this 1 electron, so that 1 electron could go in there, but then you would have to have another atom of sodium to provide the other electron for over here. So then that chemical formula would be Na2O, a 2-to-1 ratio, instead of MgO, which is a 1-to-1. All right, on this one, remember you had these little dips in the ionization energy graph. If you go back and look at the graph you made in your Google Docs, you'll see it. This is a P1. And this is a P4. So the little dips happen when you start a new sublevel or go one past half full in the sublevel. Remember, P sublevel has 3 orbitals. 1, 2, 3. That's half full. When you go to P4, you got an extra electron sitting in there, and so this guy is going to repel him as well as the others. So it's a little bit of less difficult to remove this electron here than it would have been this one. The reason, because it's being repelled by the electron that's already in the orbital. So the ionization energy dips slightly. Now, which one of these is in a P4 position or a P1 position? Well, carbon's in a P2 position, nitrogen's in a P3 position, oxygen's in a P4 position, and fluorine's in a P5 position. So the P4 is the one that's going to have a slight dip for ionization energy. So the answer was C. Okay, this question here, which one has the least tendency to gain electrons, would be the biggest one. The biggest element on here is barium, and also barium is an S2. So for 2 reasons, it's big and it's got a full sublevel. It is not going to gain an electron. All right, down here, this is the outer shell for nitrogen. 1, 2, 3, 4, 5. It's not possible, well, I shouldn't say everything's possible, but it's very, very unlikely to lose more than the electrons that are in the outer shell, and there are 5 in the outer shell. So nitrogen could lose up to 5 electrons, but the 6th electron, so if you look at it this way, 1s2, 2s2, 2p3, the 6th electron would have to come from back here. Well, that's not going to happen. So you're going to take away these 5, maybe, or these 3, maybe. But you can't take away more than is in the outer shell. So if you had a +8 oxidation state, you'd be taking away 8. That's more electrons than nitrogen even has total. You won't take away all 7 because the 6th and 7th would come from the first energy level, and the same thing for letter D, the 6th one would have to come from the first energy level. So 5 could come off, but not more. So the only possibility here is 3. All right, hope that helps a little bit. And I'll post this. And I'll see you on the day next week that I see you. What is that? Wednesday? All right. Oh, yeah, Wednesday. Whatever day we have. I can't remember what's the day and what's the B day next week.